And it looks like we are live. Hello, everyone. Welcome to tonight's session on E1 and E2 reactions. This is a continuation from SN1 and SN2 last week. So let's start with a quick sound check. Let me know that you can hear me. Let me know that you can see my screen. Nicole, it is good to see you. November 21st, so you have some time. Took one this morning and got a 96. Congratulations. And that was just from the session last week. That is amazing. Nicole, I know you're working really, really hard in this class. And so a 96 on this topic, that is really awesome. Noelle, it is good to see you from Hudsonville, Michigan. Next organic chemistry exam is November 19th. You definitely have some time, but I know you're going to be tested on quite a few topics. So make sure that you slowly but surely break down what's going on, make sure you understand it. I knew you had something sooner. There we go. A quiz over the reactions next Wednesday. That's the one to focus on for now. And another one tomorrow. Perfect timing. Is it just on E1, E2 reactions or all of substitution elimination? And thank you so much. Freaking out. What specifically are you freaking out about? And let's see if we can fix that today. I'd be chill with anything passing. Well, let's see if we can get you passing and then some. And yeah, I'm freaking out a little too, but not because of elimination reactions. My marathon is in a couple of days, as you guys know. But we are going to make the best of this in the meantime. Orgo 1 exam tomorrow feel pretty all right with all those topics and the concepts of SN1, SN2, E1, E2. But in practice, it gets a bit jumbled. So let's see if we can change that today. Because professors aren't going to start easy. They're going to throw something like this at you, where after you break it down, and realize that we can absolutely have elimination reactions. If we look at the two different situations that I have here, and I'll break it down shortly to show you how I figured it out. But this one here would be an E1 reaction. This one here would be an E2. And the only thing that's different is H2SO4, sulfuric acid, NaOH is a strong base. But all of a sudden, we get completely different products where the first one, I get a pi bond right here. And the second one, I get a pi bond right here. So what is going on with these reactions that makes something as simple as switching from an acid to a base give me a completely different product? That and shortcuts and tricks and all the good stuff that I know you're here for is what we're going to be covering with today. That's what I'm going to be sharing with you today. We're going to go through a lot, and I don't want you to feel overwhelmed as we go. I want you to focus, pay attention, try to learn as much as you can. So don't worry about taking notes. I will take the notes for you. Anything you see me writing on the screen, I will save as a PDF and email to you tonight. Just put live notes in the chat, and I'll give you the link for where to access it. Yes, even if you're watching the recording. Before we can figure out the shortcuts to get these products as quickly as I did here, we have to take a step back and let's really break down each of the reactions so that it makes sense. I want it to be intuitive rather than just something that you're memorizing, because that's not going to help you on exams. The E has a secret word in front of it. We're looking at beta. Then we can look at the E that stands for elimination. And the 1 does not stand for how many steps there are. The 1 tells me that it's unimolecular, which is really important. It tells me that one molecule is reacting at a time. Elimination is going to be the removal. Specifically, we're eliminating a hydrogen and a leaving group. The beta hydrogen is what we're removing along with the leaving group. And unimolecular tells me that it's one molecule at a time. One molecule reacts at a time, which means that this is going to be a multi-step reaction. This is very important because E2 is not a multi-step reaction, and I want to make sure you don't confuse them. A couple of things we have to look at with the molecule before we go into the reaction. I talked about a hydrogen, on the beta position and a leaving group. So what are we looking at? In an elimination reaction, we start by identifying the position of the LG. LG is simply the leaving group. A leaving group is any group that is capable of leaving and staying off the molecule, meaning it is capable of being stable in solution. Good leaving groups, for example, are halogens, bromide, chloride, iodide, or things that have charge, and when you take them off, they're neutral because charge is a burden. So for example, if you have a protonated alcohol, that's a water molecule. If you have something capable of resonance, those are all good leaving groups. And the next thing we want to look at is how to count. The alpha position, carbon number 1, is the carbon that is holding the leaving group. And attached to carbon number 1 is the beta carbon. The beta is position number 2, gamma is 3, delta is 4, and so on. We don't care about that. We care about alpha and beta because anytime we have an E1 or an E2 reaction, the alpha carbon is going to lose the leaving group and the beta carbon is going to lose the hydrogen. In this case, we have 2 beta carbons, which we'll get to in a moment, because this means we can have potential products. So how do we figure out which product is going to form? We have to understand how to recognize the more stable pi bond, because the more stable the product, the more likely it's going to form, which means we have to look at pi bond stability. And how do we tell which pi bond is going to be more stable? Noel, I think this was one of the questions you had posted, and I promised I would cover it today. So I made sure to go back to my notes and add it for you. Pi bond stability is all about substitution. Substituents stabilize the pi bond just like they stabilize a carbocation. So we'll start with the least stable, the least substituted would be a pi bond that has absolutely no substituents. That is a really good question. Remind me, because I don't have it in my notes, but I would cover it later. If you remind me, I'll show you an example. If I have a pi bond, which we'll draw like this, just a carbon bound to another carbon with no other carbons attached, that will be the least stable, because this right here is considered, well, it's unsubstituted. It has no substituents. It's not visible here, but don't forget that there are invisible hydrogens at the end of the molecule, and that's it. Slightly more stable is a pi bond that has one substituent, and this right here is considered mono-substituted. I'll show you a shortcut for it after. The next pi bond that we have is di-substituted, and there are 3 different ones, which I'll put the most stable at the top, the second most stable in the middle, and the least stable at the bottom. This one is di-substituted. Each of these 3 are di-substituted. More stable than that is if I have something that is tri-substituted, for example, like this. And the most stable is somehow ran myself out of screen here. Let me see if I can squish these things. There we go. The most stable pi bond is as substituted as can possibly be. This one right here is tetra sub, and this one right here, I forgot to put tri sub. Tri substituted, tetra substituted. I'm just writing the short words here. Shortcut in the comments if you want a very easy, fail-proof way to see exactly how to identify their substitution without having to go crazy. Here is what I like to do. I call this the highlighter trick. And that's because when you highlight the pi bond, then draw a line coming out of each sp2 carbon to another carbon. The number of lines or arrows that you have, the number of substituents. I have no carbons over here. Therefore, this is not substituted. If I highlight this one right here, I have 1 line to carbon. That's why it's mono-substituted. Same thing over here. I got 3 pi bonds, and look how many lines come out of each one. 1, 2, 1, 2, and 1, 2. That is why each of them are di-substituted. So what makes this one most stable and this one least stable? This has to do with the location of the substituents. The substituents on the cis pi bond over here are too close together. And so they kind of get in each other's faces a little. Where trans, they're opposite. They're as far away from each other as possible. And if they don't get in each other's faces, they don't raise the energy of the molecule. And this one right here, because they're on the same carbon, they're even closer. Notice they're both coming out of this sp2 carbon. That makes them the least stable. Moving over to tri-substituted, we have 1, 2, 3. I can go to both of the carbons that are sp2 as long as I can find another carbon that isn't the sp2 carbon. That helps me find the degree of substitution. And last but not least, over here, I have 1, 2, 3, and 4. If you're with me on stability of the substituents or stability of the degree of substitution of the pi bond, let me see a thumbs up in the comment, because this is going to be critical to not only understanding elimination reactions, but also the shortcuts that I'm going to show you. So going back to the molecule, let's see what happens when we try to combine all this together. We'll look at an E1 mechanism, starting very simple. If I have a molecule like this with a bromine, because the product will have a pi bond, it will be planar, meaning I won't have chirality. So it doesn't matter. I can put the bromine on a wedge, but it really doesn't matter. The first step in an E1 reaction is recognizing that the bromine is a highly electronegative atom. And if you don't have anything there to kick it out, then it just kind of hangs around there and pulls on the electron density between itself and carbon. And it pulls and it pulls and it pulls, making carbon very partially positive until eventually it pulls so hard it completely breaks away, giving me the carbocation intermediate. This right here now has a bond missing. It has an MTP orbital. This is a carbocation intermediate. And then the Br minus is off floating somewhere in solution, never to be heard from again. We don't care about it. It is stable. It is a spectator ion. Don't care about it. This right here, because the bromine pulled and pulled and pulled and eventually broke away, this is considered the slow step of the reaction. And anytime you have one step that is so slow and the rest of it is really fast, that is called the rate determining step of the reaction. I'll put rate determining step, and we'll come back to the rate in a moment. Thank you so much. I appreciate that. And Noel, here you go. Once that carbocation forms, we talked in the SN1 series, in the SN1 video, about how a water molecule, I should probably give you a solvent for this reaction. We'll put this in water. A water molecule can come in and directly attack for SN1. Here, I'm going to show you elimination. The thing about SN1 and E1 is that they're always in competition, and you can have both. I'm only showing you E1 today, but remember, this can be SN1 and E1. I'll just put also SN1 so you don't just try to limit it to E1. What happens with E1 is, well, first let's see what's going on with the molecule. I have a positive charge over there, and then I have a bunch of hydrogens on the nearby carbons that happen to be there. We don't draw the hydrogens, but for the sake of this, I want to explain what's going on. Carbon is very positive, but as a secondary carbocation, part of what stabilizes it is that there is almost orbital overlap going on from the nearby groups. And so some of the negativity from the hydrogens are kind of being pulled to stabilize that carbocation, which means that the hydrogens are left feeling ever so slightly partially positive. And when that happens, a molecule like water can fully take advantage of that situation, reach out, grab a hydrogen atom. If hydrogen can only have one bond, this bond collapses in the direction of the carbocation, in the direction that it's already being pulled. And what we get as a result in this case is the hydrogen that disappeared, that was this one. The electrons that were left behind are now sitting here and here as a pi bond between the two carbon atoms. This right here is the beta elimination. We started with the leaving group at the alpha position. We grab the hydrogen from the beta position, and that right there is my product. Is that the only product? And if it's not, how many other products can I potentially get in a situation like this? While you're typing that in, I'm going to talk about the slow step again, the fact that this is a rate determining step. The rate of an E1 reaction is equal to some constant K, specific to which reaction we're looking at, times the concentration of the molecule that is holding the leaving group, the alkyl halide. And that is it. This is the only step that matters. The way you can picture this, the idea with a slow step, imagine that you're driving home and you went somewhere that was 10 minutes away. And on the way home, you got stuck because there was some kind of accident or a tree came down or something. And that one tiny section of road took an hour because there was no other way to get around it. Whatever the reason you got stuck, you can't go anywhere. You're stuck for an hour. The moment that thing is cleared away, it takes you about 5 more minutes to get home. That hour, that's the slow spot. So you say it took me an hour to get home. No, it took you an hour and 5 minutes, but we're rounding about an hour because the rate determining step, that slow step, pretty much tells you how long the whole thing took. That alkyl halide, the speed at which the carbocation forms, that is the rate determining step of this reaction. Now, going back to the products, I can have not one, not two, I can actually get 3 products for this reaction. But first, we have a question. Can you repeat why the hydrogens would have negativity? No, the hydrogens are partially positive. If I said negative, I misspoke. The hydrogens are partially positive because the negativity is being pulled away from them. And as it's being pulled away, they are left feeling ever so slightly positive, and that is why they get grabbed. The first product we saw here, the second product requires us to remember that this right here and this right here, these are sp3 hybridized carbon atoms, and they can rotate. They don't have to stay exactly where they are. And so if the molecule rotates, I can get another product where, I'm going to give you the simple explanation now, and then we can go into detail later because students had asked about the periplanar stuff. So I'm going to get, what I like to do is start easy and make sure you're with me and then build it up, make sure you're with me, build it up. So we don't go from here's a reaction, now go learn all the craziness and have fun with it. The last one is to realize that this right here had the hydrogens over here, but we also have beta hydrogens over here. And if the base, the water molecule, happened to come in and attack from the other side to grab one of these hydrogens, then the pi bond would have formed on the other side, and I would have gotten something that looks more like this. And that is how I get a total of 3 different potential products for this reaction. Now, your professor is likely going to ask for all the products, then ask you to rank them based on which is more and less stable. So let's go back and review the ranking. The more substituted the pi bond, the more stable it's going to be. The less substituted the pi bond, the less stable it's going to be. And we'll use the highlighter trick on the products to figure that out. So in this case, if I highlight each of the pi bonds, I want to see how many lines come from the sp2 to other carbons. Here I have 1. This is mono-substituted. Here I have 2, and here I have 2. These are both di-substituted. The difference is this one is a cis-di-substituted. This one is a trans-di-substituted. We already talked about how trans is more stable, making this one right here the major product. Major product means it's most stable, faster to form, and much more likely to form. This one right here is considered the minor product because it's slower to form, therefore least likely to form. If this one takes a second and this one takes an hour, by the time the hour is done, most of the product's already reacted. in the version that took a second. And we're talking about way, way less than a second, but I'm trying to give you just time amounts that we can actually process. And so your professor will want you to show the major and minor product. Question: how do you know that the second one is cis and the third one is trans? Oh, very good question. Let's go back to the pi bond area and talk about that right here. So the two types of pi bonds you're asking about are if I have a trans pi bond and a cis pi bond. Everything about them is the same. Notice we have 1, 2, 3, 4 carbons, pi bond on 2. 1, 2, 3, 4 carbons, pi bond on 2. They're both 2-butene. The difference is where the groups are sticking out of the pi bond. For the first one, I have my pi bond in the middle. For the first one, you'll notice that they are in opposite directions. This is considered a trans pi bond. And the way that I think of it is trans as if they transferred away from each other. They transferred to the opposite side. Where cis, I think of it like sisters. They're on the same side. You see how the arrows are pointing on the same side together? That makes this a cis and the other one trans. Noelle, great question. Let me know if that makes sense. Let me know if that's clear. And yeah, we have an answer here. Excellent. So let's go back to this product. Now, this may take a little bit of getting used to, and that's why the key here is to do lots and lots of practice. Today, I'm focusing just on the simple reactions so that I can teach and explain the concepts. But to get a lot of practice, make sure, if you don't have it yet, to grab my substitution and elimination midterm practice worksheet. This is called the Leo and Nuts and wrote multiple pages of practice problems on substitution, elimination, and then combining them all together. It's not available on my website, but if you put midterm in the comments, I'll send you a link to grab it. And you can just do tons and tons of practice to make sure that what you learned today actually makes sense. Noelle, excellent. All right, so now that we have the basics for this reaction, the way that students typically solve this is to, sorry, I'm distracted looking in the comments. The way students typically solve this is to draw it out and draw the whole mechanism and draw all of them. But sometimes your professor will give you a problem like this. And they'll say, in this situation, show me the major product when this right here reacts with, let's do H2SO4 and H2O. We're only looking for the major product. Put shortcut in the comments if you want to see a faster way to get this without having to draw them all out. First, I'm going to break down some of what we see. Typically, you have your reactant at the top and your solvent at the bottom, your reagent, I'm sorry, at the top, the thing that does the attack. And with an elimination reaction, we talked about how it's something that grabs the proton. That means we're looking for a base. But if you look at what I gave you here, this is H2SO4. This is not a base. This is not something negative or partially negative. It's an acid, sulfuric acid. It's got acid right there in the name. So what in this reaction is going to attack to allow that elimination reaction to take place? H2SO4 is a proton reservoir. Yes, exactly. It's a source of protons in solution. It's an acid catalyst. If you have a reaction where you don't seem to have a base, and the opposite, you seem to have an acid, look at your solvent. Your solvent, in addition to being the liquid that everything is dissolved in, can also be a solvolysis reaction. Solvo, solvent, lysis, breaks. This is the solvent breaking, attacking, interacting, whatever you want to call it. The solvent is also the attacker. And so in this case, just like the reaction I showed you up here, notice that I said water does the attack. Water is the base in this reaction, and it's a weak base. It doesn't have a charge. It's not very reactive. And so it's slow. and it waits and it waits and it waits, but we're not going to do the mechanism because I see many shortcuts in the comments. Here is your shortcut for coming up with just the major product in an elimination reaction. First, you'll identify your alkyl halide, cross out the leaving group, and redraw the chain exactly as you see it. And I purposely put a ring here because for some reason, professors love to scare you with these rings. Let me know in the comments if me drawing that benzene made this problem look so much harder. You redraw it exactly as you see it without the leaving group. Then you quickly identify that this is your alpha carbon, and therefore we have a beta carbon here and another beta carbon here. Now here is what I'm looking for. Actually, to show you the shortcut, I'm going to need to do an easier problem first and then show you the harder problem because I want you to follow me. Wait, no, let's do it like this. Okay. We'll put a bromine right here, and we'll give you the same reaction conditions, which is H2SO4 in H2O, source of protons, and that's my solvolysis. Identify and cross out your leaving group. Redraw the carbon skeleton exactly as you see it, but we already know that this is the alpha carbon. Let's identify the beta carbons. Right here, we'll make this a light blue beta carbon, and we'll make this one a purple beta carbon. If I were to draw both of the products, let me show you the shortcut here. If I take a hydrogen from the light blue, so let's, instead of putting beta, we'll actually draw the beta hydrogens in. If I take one of the light blue hydrogens, then the pi bond will go here because the pi bond goes between the alpha of the beta and the alpha carbon. If I swap out the purple for hydrogens, then the pi bond, if I grab this one, will go between beta and alpha. That would go right over here. I could take the time to figure out the substitution, or I can not even think about that and look back at the starting molecule. The carbon holding the purple hydrogens is a secondary carbon. The carbon holding the light blue hydrogens is a primary carbon. How did I know? Look at the carbon and see how many arrows come from that carbon to another carbon, just like we did with the pi bond. So here I have only one. That's how I know it's primary. And here I have 1 and 2. That's how I know it's secondary. Now here's the shortcut. We can look at this and see that this is major and minor. And anytime you have a trans, just remember to also draw a cis because both are a possibility. Plus this and plus that. This was the long way. The short way is to say, if this is a secondary carbon and these are secondary hydrogens, the more substituted the carbon, the more substituted the hydrogen, the more substituted the resulting pi bond. And so that means a secondary beta carbon is going to give me a more substituted major pi bond product. Let me know if that made sense. So fire emoji in the comments. If I grab a hydrogen off a more substituted carbon, the resulting pi bond is going to be more substituted than if I grabbed it off the other one. Noelle says, my professor put some rings on the exam last week. So Noelle, I challenge you to ignore the rings. And I'll show you in a moment how we can do that. I swear my professor invents giant molecules with 4+ rings for every question. The key is to look past the rings and ask yourself, what is the science of the question? And that is the only thing you need to look at. The only students who got a benzene carbocation stability question, so not so much anymore. Okay, I'll take it. I hope that that means that you learned how to look at the science behind the ring. And let's apply that right here. There's a benzene ring. There's a lot going on. Don't care. This one right here is a secondary beta carbon. And that means it has secondary beta hydrogens. This one right here is technically a tertiary beta carbon. So it would give me I probably should not have done that. I meant to give you an easier question. I apologize. This is a trick. This is a tertiary beta carbon, except for the fact that it's not the beta carbon I care about. It's the beta hydrogen. The secondary beta carbon has 2 hydrogens. The tertiary beta carbon has no hydrogens. There are no beta hydrogens on this carbon. And if there's no beta hydrogens to grab, there's no beta hydrogens to eliminate. And, well, the only pi bond possible is right over here. I did not mean to give you such a hard problem. I got carried away with the ring. So this was a trick I was kind of going to show you later. But hopefully that still made sense. Let me actually show you the problem I had in mind so that we can kind of redo this as an additional practice problem. In this situation now, we do have a hydrogen right here, and we have hydrogens right here. Now let's evaluate it for what it is. We redraw the skeleton as we see it without the leaving group, identify that the green beta hydrogens are secondary. The purple beta hydrogen is tertiary. Tertiary is more stable or more substituted than secondary. Therefore, putting a pi bond between the alpha and the tertiary beta is going to be the major product because the pi bond is also going to be the most substituted. That is a very good question. Remind me at the end because that'll be a fun one. Yeah, let's do that. Any questions on the E1 reaction so far? Go ahead and write it down. Just looking back at my notes, I realized that I forgot to label this. The major product and the idea with more substituted pi bonds comes from the scientist Zaitsev. And so the most substituted pi bond is called the Zaitsev product because of Zaitsev's rule. Zaitsev's rule says that we form the most substituted, most stable pi bond in an E1 or E2 reaction. Another thing that I didn't show you is that in a lot of elimination reactions, you're going to see a triangle or heat or some other way of implying heat. And what this does is heat simply helps the reaction because elimination has a much higher activation energy than substitution. And so adding heat just helps you get to that activation energy faster, and it helps the reaction. One more type of E1 reactions that professors are going to ask you to know, and this is going to show up a lot in the later reactions once we get to the chapter on alcohols and more. And I actually included that over here in the open. Nope, that's not what I included in the open. So let's do, I thought I had it there. Let's just do a simple version right here. And we'll start with an alcohol. If I take an alcohol and I react it with H2SO4, water, and you'll often see heat in this reaction. This is a very specific type of E1 reaction. This is called the dehydration. And when you're thinking of dehydration, what are you thinking of? Would this method work for any E1? If you're talking about dehydration, that specifically will take place with acid and water. But if you're talking about the shortcut in general for the E1 product, that works for any elimination reaction. Dehydration is the removal of water, a molecule of H2O, 2 H's, and 1 O. So yes, we're removing H and OH. Water is being pulled. Let's see how that happens. We have a source of protons in solution. We know that the first step in an E1 reaction was the leaving group leaves. Except if I somehow, some way managed to make this leaving group leave to give me a carbocation and an OH minus, there is no way, absolutely no way, that I am forming a negative charge in an acidic solution. Acid is positive. It does not allow negative to form in solution. OH minus is a bad leaving group, and the definition of a bad leaving group is it's bad at leaving. It does not leave. So the absolute first thing we have to do is kind of like my toddler when we want to make him do something. So I just Googled the definition of toddler, and apparently I don't have a toddler because I have a 3.5-year-old. My baby grew up too fast. But when I want him to do something, I am not above bribery. And that's what we have to do here to the OH. The way we bribe an electronegative atom is we give it something positive to latch onto, and that is a proton. Protons make really, really, really good bribes because now I have an O, an H. The green electrons that reached out are now sitting as a bond between themselves and that red hydrogen. Now I have an OH2 with a positive charge, an oxonium. Oxonium is a great leaving group because it's charged. And when it leaves, because it is positive, it has regrets, and it now starts pulling on the bond just like the bromine did in the previous reaction. Now we get a carbocation right here. And then in solution, we have a water molecule that is neutral. Unlike the OH minus before that was not stable, this is perfectly happy. I missed the electrons there. Let's make these light blue, so they'll be right here. This is happy. It's a good leaving group. It stays gone. And now we have a carbocation. This was the slow step. The moment that carbocation forms, the moment water breaks away, a solvent molecule is going to take advantage of the situation and attack. Now, if you're asking me, so does that mean it's in competition, substitution, and elimination? If it attacks right here, it looks like substitution, but wait, that would just give me this right here, which gives me this right here. So dehydration is specifically an elimination reaction because substitution is just going backwards. So what'll happen is one of the water molecules will find the most substituted, most stable hydrogen to grab. That will be this one right here. This one is secondary as opposed to this beta, which is primary, less stable. Grab a secondary hydrogen, collapse the electrons back. And now I'm just going to show you the major product. We have a pi bond between the alpha carbon, the more substituted beta for the most stable product, a pi bond in place of, notice what I have pulled away. I had an O and an H, and then I pulled an H from here. HOH, water. That is the dehydration E1 reaction. Know this, recognize this. As soon as you see this setup, H2SO for H2O and heat, dehydration. Any questions on this so far? Go ahead and type it in. Even if you're watching the recording, I do go back to the comments. And then if there are no questions, or even if there are, let's move on to E2 and I'll go back and check for the questions. E2, once again, has the word beta. The E stands for elimination. And the 2 stands for not the number of steps, the number of molecules. This is a bimolecular reaction. Bimolecular meaning 2 molecules reacting together at the same time. Elimination is hydrogen and a leaving group leave. Beta tells us the position of the groups that were, well, the relationship between the 2 groups that were kicking out. The key for an E2 reaction, the thing you absolutely have to know is that we are dealing with 2 molecules colliding, interacting at the same time. This is a one-step reaction. And if there's a one-step reaction, what is the chance of getting a carbocation intermediate? Question, is there a major minor for that example? For this last one, yes, there would be major and minor. I only gave you the major product. But remember, if we have trans, we also have cis, and we could have also had the non-Zaitsev, sometimes called the Hofmann product. So this right here would be minor, and this right here would be the middle product. Back to the one-step reaction. if you take nothing else away from this session, except for there are absolutely no carbocation intermediates you are already ahead of the game. No carbocations intermediate. There we go, 0%, because a carbocation intermediate has the word intermediate. If there is a one-step reaction, there are no intermediates because everything happens at once and there will be no carbocations. So let's see how the E2 reaction works. If I have a starting molecule like this, similar to what we had before, and I react it with NaOH and H2O, let's add heat because why not? Instead of the bromine leaving by itself to give me an intermediate, we have a very, very strong base. Anytime you see a sodium, a potassium, a counter ion, a spectator ion simply there to balance, get rid of it. And A+ tells me it's countering an OH-. And the thing about that OH- is that charge is a burden. And if charge is a burden, it is unhappy, it is unstable, it is strong and very, very reactive. It is so reactive, it's not waiting around for a leaving group to leave. It is having a bad day. It wants what it wants, and it's going to make it happen. So the OH- is going to approach the molecule and decide which hydrogen it wants to get, secondary or primary. Secondary is more substituted, more stable, major product. So let's show both. If it happens to grab the more substituted hydrogen, hydrogen gets attacked. The electrons collapse towards the pi bond, and that is what kicks out the leaving group. We're going to get this product right here. Or we can also have gotten the molecule twisted and get this product right here. But if the OH- came and grabbed the less substituted primary primary hydrogen, grab the hydrogen, collapse the electron, that kicks out bromine. What I get in this case is a pi bond right here. These two are di-substituted. This one is mono-substituted, making this one the minor product. This one the major because it's trans, and this one the middle because it's cis, but still more substituted. So that is the quick version of the E2 reaction. The same shortcut applies, where if you don't have to draw them all, if you're just asked for the major product, then you can look at the degree of substitution. The hydrogens in light blue are secondary, light green is primary, secondary is more substituted. It'll form more stable, and all you had to do was draw this one in one step to get the product. Are you able to show examples that you draw in the transition state? So let me show you what this would look like for the same molecule. Let me just see what we have. Okay, I think I can draw it right here. If this is what I have, and we had the hydrogen here being grabbed, what color did I have for bromine? Blue. We have the bromine right here as it's leaving, and I'll show you an OH- as the base. The transition state is going to have all of the bonds being formed and broken at the same time. The bond between the hydroxide and the hydrogen is being formed. That means this charge is partially negative as that negative is disappearing. Where does that negative go? I didn't show you that in the products. Let's take this one right here. I have an O, I have an H, and then I have the H that it grabbed right there. So that's a water molecule that's neutral. And so we're going from having a negative charge to having a neutral charge. That's why it's partially negative. The bond between hydrogen and the molecule is slowly breaking away. The bond between carbon and bromine is slowly breaking away as the pi bond is starting to form. Bromine, which is neutral, but as it breaks away becomes negative, is going to be partially negative. So this would be in one step, all of the intermediates, bonds being broken and formed, and then in one single go, they all finish and you get your final product. That was a really good question. So let me know, Megan the Stallion fan. I like that. I like your handle. So Megan, let me know if this answered your question. Can you do a dehydrogenation example with alkyl halides? So dehydrogenation, let's go up here, right here. Dehydrogenation. Wait. Dehydrogenation would be removing hydrogen. So this is kind of a dehydrogenation, but are you asking about a different reaction? Let me know what specific reaction you're asking about, because either I'm not understanding or my brain is just skipping out on me for a moment. Excellent. So there were a couple of questions about anti-periplanar. So I want to go into this. Whoops, I don't want to erase that. I want to go into this in a little bit more detail and show you exactly what is actually happening. When this right here happens, the elimination is simply a series of dominoes that fall into each other. And you don't see it here, but if I have, let's see, this is the carbon in question, and we'll show the hydrogen, we'll show the leaving group, and we'll show the base. When the base grabs the hydrogen, what is happening is you have the orbitals collapsing. They're sort of being pushed into each other, like one domino hitting the next, hitting the next, hitting the next. And so this will grab the hydrogen. These electrons will collapse this way. These electrons will collapse this way. Do you see how they're all going in a straight line? This is really, really important. Hydrogen and bromine must be anti. They must be opposite from each other so that the orbitals can collapse into each other to kick out the leaving group. If they're not lined up, it's like you're pushing this way and you're trying to knock out something that's that way. You're not going to hit it. The momentum is not going to what's the word? The momentum is not going to carry you in that direction, and it's not going to happen. So for example, if I have a situation where the hydrogen is like this and the bromine is like this, and I have my base and it's reaching for the hydrogen and the electrons want to collapse that way, but this is going to fall in that direction. It is not going to fall in that direction. This will give you no E2 reaction because the bromine is facing in a completely different way from where it has to go. Let me know if that makes sense. And I want to demonstrate that in, let me think of how to show this to you. A very common example that professors are going to get you with this is in a ring. Say I have a bromine right here. And on one side, I have a methyl coming out of the page. And on the other side, I have an ethyl going into the page. Degree of substitution for the hydrogens, this green one is tertiary. And this blue one right here, not a 3, this blue one right here is also tertiary. So everything about them looks the same. And the question is, which hydrogen am I going to grab for this product? The answer is not 2 products. There is only one right answer, and professors are going to trick you with that. So here is the best way to see this. Take your chair conformation. Oops, I kind of gave it away. Take your cyclohexane and redraw it as a chair conformation. So if I redraw it like this, the chair does not have to be pretty. It just has to be obvious. It doesn't matter how I number it as long as I'm consistent. Clockwise has to stay clockwise and counterclockwise has to stay counter. So I will call this 1, 2, and 3 in the clockwise direction. And so that means I will call this 1, 2, and 3 also clockwise. On carbon number 1, I have a methyl in, hold on, I'm going to have to draw some lines on here. Okay, this is just a quick way for drawing a chair so you know exactly what's going on. For carbon 1 methyl in the up position, we see that is going to have an equatorial. What I just did here, I teach this in my chairs video. So if you put chairs in the comments, I can give you a link. Let me just make sure I have the link. And yeah, even if you're watching the recording, if you put chairs in the comments, I will send you the link. Yep, okay, I found the link. And that will just teach you how to quickly draw this so that you're not wasting time trying to figure out what's going on. For carbon 2 in the up position, I have a bromine. For carbon 3 in the down position, I have an ethyl. And by doing this quick chair, I knew where to put my axials and my equatorials. And then let's fill in the hydrogen. Down on carbon 1, up on, down on, wait, sorry. Carbon 3 is up. Trying to remember my ups from my downs. All right, here we go. Now it is very, very easy to see what's going on. First, I want to point out, I was very intentional to put my leaving group in an axial position. The leaving group must be axial because if it's equatorial, it's sideways. And if it's sideways, I cannot kick it out. So I put the leaving group in the axial position. If the way you drew your chair did not give you the leaving group axial because you didn't know my shortcut, just redraw it and move the numbers over. That's fine. You could draw it as many times as you want. Now that the leaving group is axial, notice that the blue hydrogen does not allow for an anti-periplanar reaction. If this goes down, right, that's the direction of the electrons, we can't like suddenly turn and get that bromine, the leaving group in the up position. But for the green one, we can come from the bottom, grab up. Hold on. I'm going to have to exaggerate this a little bit so you can see. But notice that straight line that is happening. Grab, grab, out. Boom. They all go in a row. That is how I'm able, you're very welcome. That is how I'm able to kick it out. And so by drawing in a chair conformation, you're able to very obviously see which hydrogen you're going to grab and which product you're going to draw. Now this is a very long and tedious way. So put shortcut in the comments. If you don't want to draw the chair conformation on your exam, you don't want to bother with the chairs at all, and you want to make sure you're right 100% of the time, because I have a good shortcut. Of course, I have a shortcut. I don't want to do this work the long way. In looking at this, here is what you want to identify. The reason I knew to grab the green hydrogen and not the blue one is because I had to make sure that my hydrogen and leaving group were perfectly lined up. What does that mean to be perfectly lined up on a chair conformation? I'm looking at two things. One, they must be trans to each other. Trans, like we talked about before, opposite. One has to be up, the other has to be down. They cannot both be in the same direction. Leaving group and blue hydrogen, they're cis. They're both facing up. But this one and this one is up, one is down. They must be trans. And the second trick, not the second trick, the second piece to this is they must be axial. Axial means straight up, straight down. You get that perfect line with kicking it out. So if they are trans and axial, you know that they're lined up for an elimination reaction. Axial, you only see on a chair conformation though. So we're going to get rid of number 2 because that's too much work. Hydrogen and the leaving group must be trans. So now let's completely forget about our chair conformation. And let's not cover the rule. Let's just forget our chair conformation and look back at our original molecule. If I have my leaving group is up. That means I am looking for a hydrogen that is down. This one is up. That's no good. This one is down. That is good. Hydrogen and bromine are trans to each other. That is how I know which one I'm going to grab, and I never have to bother with a chair to begin with. So then, to draw the product, let's do just NaOH and H2O, because why not? Redraw the skeleton exactly as you see it, minus the leaving group, with one caveat. If I grab a hydrogen from any position, that is going to change. So let's hold off on it. Redraw everything else on the chair, which means this right here stays where it is. I will put dashes to the ET. I don't have to show the blue hydrogen. Hydrogens are invisible in line structure. Put a pi bond between your alpha that you're grabbing, the alpha for the leaving group and the beta that you're grabbing. So in this case, I'll put the pi bond right there. And then the one change that you have to make is that instead of putting this on a wedge, we now have to put it on a straight line for the CH3 like this. And the reason for this change, this right here is an sp3 hybridized carbon. If it's sp3, I have 3 dimensions, dashes, wedges in the plane of the page. But this right here is sp2. sp2 is flat. Trigonal planar, just flat. That means there are no dashes, no wedges, just plane of the page. And so make sure not to draw this as a wedge, just to draw it as a straight line. And there's your final product without having drawn the chair at all. Question: what if the CH3 was on a dash? Then you would have no reaction, because if both of the hydrogens are cis to the leaving group, then it will not undergo E2, but it can undergo E1. The reason it can undergo E1 is with E1, we have a carbocation intermediate. The carbocation is flat, and then you can grab any hydrogen nearby. It doesn't matter. If I have that same starting molecule for an E1 reaction, let's see if I can grab a somewhat cleaned up version. Let me show you. Did somebody else ask me for a different reaction before? I just want to make sure I cover that before I forget. Okay, so let's take a look at this right here. But now we're going to change it up. We're going to do E1. So for E1, I need a weak reaction. We'll do solvolysis, H2SO4, and we'll put it into CH3OH, a different polar protic solvent that also does solvolysis. H2SO4 is the source of protons in solution. That means it is acidic, it is weak, it is slow. That will be an E1 or an SO1 reaction. Today, we're just looking at E1. The leaving group leaves. That means for my intermediate, I have a carbocation right over here. And then, oh my goodness, this is a mess of a problem by accident, and I'll show you why. I have, a ring expansion. Somebody wanted a ring expansion. I have a CH3 here, and I have an ethyl here. Here's the problem with this question. There are going to be a gazillion products here, which I don't really want to draw out, so I'll just kind of talk through it. Right now, I have a carbocation sitting right here at the secondary position. What is going to happen next is another trick that I wasn't planning to teach today, but why not? Let's bring all the tricks, not the trick as much as a thing to recognize. Anytime you have a secondary carbocation near a tertiary carbon, you will get a carbocation rearrangement. Specifically, you're going to get a hydride shift. And that means I can take the hydrogen from here, or the hydrogen, I did not mean to invert their colors, but whatever. The hydrogen from here can all shift over. I'm going to do one of the many. And if I have that hydrogen move over, then my hydride shift is going to look like this, one of the two options. This is now planar. The hydrogen in blue up and down doesn't matter because that was planar. The ethyl group is still where it was. And now I have a carbocation. Now here's the problem. So in this molecule, I have the gray hydrogen that was there, the blue one that just moved it over, and we have the orange ones on the other side. If this right here is my new alpha, I have beta and beta. They're both secondary. They're both equal. I can have two potential products, meaning I could put a pi bond here, or I can put a pi bond here, or I could have done a hydride shift here because it'll give me the same exact stability, which means I could have done a pi bond here and here. So I could have ultimately done a pi bond here and here and here and here. 4 products. I'm not going to draw them all. I challenge you for homework to draw them to make sure that you understand what the can of worms that I just opened. But hopefully that helps if your professor does something. Look at what you've done. You made me teach tricks and confusing questions. Don't get me wrong. I like these. So I know I didn't quite answer. No, I did answer your question. So I answered your question, and then I ran away with it. But let me know if that helped. Please do more polar protic solvent reactions. So this right here is a polar protic solvent, but I could have done anything. I could have used methanol, ethanol, isopropanol, whatever. I wish there was a 1, 2, 3, 4 point way to learn these. It seems like so much to remember. 1, 2, 3, 4 means I want to memorize it. I challenge you not to memorize it. Just understand. So what is happening with the reaction? E1, leaving group leaves, carbocation forms, you eliminate the hydrogen. E2, leaving group doesn't leave on its own. The base attacks, grabs the hydrogen, forms the pi bond, leaving group leaves. And then these are just all the different conditions and situations that you have to know. Now, I accidentally got into some harder topics today, but on the midterm worksheet that I mentioned before, the one that's not available on my website, but if you put midterm in the comments, I will send it to you. You will have beginner to advanced practice problems, and this will give you an opportunity to really see it from every angle. You start easy, then you do another one and another one and another one. And at some point, you have done so many that you know exactly what is happening because you're thinking, I just saw that and I just saw that, and here's a twist, but I just saw that. That is how you get really good at it. All right, so ring expansion. Ring expansion. I feel like that would be better in an SM1 reaction. So I will remind you, SM1 and E1 in competition. But let me see what I can do. Say we have something like this. We'll keep it simple. We'll do this right here. Ooh, I have a good one. Okay, I like it. You guys, when students email me and say, I wish you were my professor, I tell you to be careful what you wish for because I get excited over problems like this. So I'm going to argue you don't want me as your professor. You want me as the person who gives you quizzes and worksheets with answers before you see your professor's exam, because I'd be very tricky. All right, so what do we have here? If I analyze the situation, we'll recognize that we have H2SO4, an acid catalyst in heat and water, an alcohol, which is a bad leaving group, but this entire setup immediately screams dehydration, which we know is an E1 reaction. So let's go for it. The first step in a dehydration, alcohol is a terrible leaving group, and so we have to bribe it. We have to protonate the alcohol. This is called, I don't want to draw this a million times, so let's do that. And when I protonated, I have my O and H. Only one lone pair of the two remains. And now I have a hydrogen and a positive charge. I just turned a bad leaving group into a very good leaving group. And because it's a good leaving group, well, it leaves. It leaves, goes to mingle with all the other water molecules, never to be heard from again. And in its place, or what I'm left with now, is just a carbocation right over here. This carbocation is at a secondary position, but it's not going to stay at the secondary position because this right here is a tertiary carbon. In the last trick, I told you that a secondary carbocation near a tertiary carbon will do a hydride shift unless you have a ring. So here's another bonus trick for you that I did not have in my notes for today. If you have a secondary carbon near a 5 or 7 member ring, I want to say 4, 5, or 7, you're going to get your ring changing, but I'll keep it now for the 5 because a 7 is a contraction, which probably not going to learn. But a secondary carbon near a 5 carbon ring, you're going to get a ring expansion. Instead of just a hydride shift, you get a completely different carbocation rearrangement, and that happens like this. There's symmetry in the molecule. It doesn't matter which one I choose. But one of these carbons that is bound to this right here is going to break. And it's going to form a new bond to the carbocation. I'd like to redraw it like this exactly as I see it with the dots because it can get really, really overwhelming. Once you get confident with it, you can start just numbering and redrawing that way. So let's see exactly what we have. Let's number it. We have 1, 2, 3, 4, 5, 6, and 7. What changed, and we're going to move this up here so we have room to draw. What changed here is that the bond between 3 and 7 is now a bond between 2 and 7, like this. I have 6 and 5. That's 7. That's 4, 3. No, 3 goes like this. 3, 2, and 1, right? This was my molecule before. But now I have a new bond right over here. This is the bond that I used to have. This used to be a carbocation, but now there's a bond there, so it's no longer empty. It doesn't have the empty p orbital anymore. Carbon 3 used to have a bond, but it got nothing in return. So now this is a carbocation, and this kind of looks like a mess. So if we redraw it and recognize, oh yeah, this right here is a 6-membered ring. If you do this on your exam, please write the word redraw. I've had a student lose points because the professor said that's not a step. It's not a step. I'm just redrawing it because it doesn't look pretty. So when I redraw it, let's number it again to make sure we know what's going on. 1, 2, 3, 4, 5, 6, 7. And that means 2 is this one right here, right? And then attached to that, I have 3, 4, 5, 6, 7. Coming out of 2, I have carbon number 1. And then 3 has the carbocation. That's right here. This was the scary part. If you followed me and the numbers, then the rest is just pretty straightforward. I have a secondary carbocation right there near a tertiary carbon. That means I will have a hydride shift. Hydrogen shifts over. That gives me, I'm going to stop numbering it at this point just because it'll make it easier. This gives me a molecule that now has a carbocation at the most substituted position. I'll show you the hydrogen that moved, but we're not going to show it again. Now, water says, okay, all the drama is done. You guys are done shifting and moving and fighting. I'm ready. Water comes in. Oh, no, we're not doing substitution. I'm sorry. We're doing elimination. This is a symmetrical molecule, so I can grab that hydrogen or I can grab one of the hydrogens here. It doesn't matter. They're exactly the same. A water molecule will come in, grab that hydrogen, collapse the electrons towards the carbocation, and that gives you your final product, which is a pi bond right here. And notice that it looks very much nothing like the starting molecule because of the ring expansion. All right, so whoever asked that question, and Nicole, thank you for reminding me. I hope that helped because professors love it. I challenge you and give me 2 thumbs up in the comments to redo this 3, 4, 5 times until you feel so solid with it, because then you know that you know it. Vanessa, I covered this last week. Email me and I'll send you the link. All right, so this was a lot to take in, but as I told you in the beginning of the session, you did not have to worry about writing everything down. I took the notes for you. Just put live notes in the comments for a PDF copy of today's session notes and midterm in the comments for my SN1, SN2, E1, E2 midterm practice worksheet. I'm telling you, it is a lot. You will feel so much better after working through the gazillion questions I have on there. It's not available on my website, but just put that in the comments and I will send you the links. Yes, even if you're watching the recording. Now, if this material here finally made sense, and you want to dig even deeper into the topic of substitution and elimination, then I want to show you something. Let me get this right here. Okay, let me know if the screen changed. Yes, it did. Okay, perfect. So this is a peek inside my organic chemistry study hall, where I teach you all of the topics you need for Organic Chemistry 1 and Organic Chemistry 2. Today, I'm specifically showing you substitution elimination, because if you want to take this further, here's what you have access to. First, an introduction to SO1, SN2, E1, and E2 reactions. And then, because this is a topic that takes time to learn bit by bit, I have an SN1 session, an SN2 session, an E1 session, an E2 session, and it continues, and it continues. Energy diagrams for substitution elimination reactions, chemical reactivity for SN1, SN2, E1, and E2 reactions, and of course, your professor's favorite, how to choose between SN1, SN2, E1, and E2 reactions. So let's randomly go into E2, because that is one of the topics we covered today. For every session, you will have a quick, oh, there are no timestamps for this one. So I have someone working on the timestamps, therefore I don't have them all, but let me go back to, okay. So for most of the videos, I want to say 95% at this point, and I have someone still going through them, and these are done manually. So if you need a specific topic, then you could see where it is in the video, or you just watch the entire session. If you click on the top right there, you get the PDF notes. Why is it uploaded twice? Okay, I'll have to, whatever, it's the same thing twice. But you get the full color PDF notes for the session. And that actually downloaded to my computer instead of opening. So it basically looks like today, same idea, full color PDF notes for everything. And if I go back to here, any questions that you have as a study hall member, you also get access to the Q&A space where you can post your daily, there's the MCAT, there's the Orgo. You can post your daily study questions right there, whatever it is as they come up. So there's study questions, there's share your wins, and a student lounge, just because this is a difficult course and who wants to go through it alone? If you can go through it and commiserate and collaborate with other students. You also have worksheets and practice quizzes and a couple other bonuses that I'm just not going to go into right now. But all of that is part of the Orgo Study Hall. And if this is something that you're interested in, you can sign up right here with the link on the screen, layerforsight.com/join, and you get instant access to everything I showed you and some more. All right, questions on what I covered today. I think I saw some questions. Can you scroll down just a bit? I didn't see when you typed that, so I don't know what you're asking me to scroll down with. Noelle, you have the study hall and the marathon bundle, so you are set. The only thing you need right now is time, because you have so much. And Noelle is a study hall member, so Noelle says the study hall is very helpful. Thank you so much. One reason I think you're finding it helpful, Noelle, is because you're actually posting questions. You're asking, you're getting guidance. I saw that one of the TAs sent you videos earlier. I added to that, so that is how you get so much out of it. Awesome. So any other questions you have, go ahead and type them in. Once I log off, YouTube keeps me connected for a couple more minutes, and then I'll just hang out in the chat as I'm working on getting the notes and everything ready for you. That will be out within the next half hour. And if you're interested in the study hall, the link again is hiding. Where's the link? right there. The link is laterforsi.com/join, and I would love to see you there. Have a wonderful evening and take care.